So I've been getting a couple questions that are fairly related to each other in regards to this idea of hypothesis testing. So I'm going to take a few moments to put this together to give you a few pointers. Really, the questions are centering around two general concepts. Number one, the question was asked, I can do the calculations, I can follow the formulas, but once I do that, once I calculate the z-score or the t-score, how do I know whether to accept or reject the hypotheses and which one? And then furthermore, what's the difference between a one-tailed and a two-tailed test? So I'm going to address that generally, and then we're going to take a look at two examples. So from a general standpoint, one-tailed versus two-tailed, what this essentially is doing is we're using the normal curve as a way to gauge how far away from what we expect is too far away. So often we're comparing something to a population or to an assumed hypothesized value or reality. That's always going to be the center. And then we've got this alpha value that is something like 0.05 or 0.1 or 0.01. This drives how far away is too far. And between two-tailed and one-tailed, you'll see how it's treated differently. In a two-tailed, let's say we want alpha to be 0.05. Well, that's 5%. What we have to do is we have to split that 5% up into two different chunks, into 2.5%, so 0.025 over here, and 0.025 over here. So that makes up the total of 5, but because it's two-tailed, it gets split in half on each side. So when I go to find the critical values here and here, which are going to define the region of everything in here is going to be okay, everything out of here is going to be too far away from what I expect here in the middle to say that it's the same. Okay? So when I have the two-tailed test, that alpha value gets split in half. As opposed to, we'll come back to this and do an example, as opposed to a one-tailed test, that alpha value stays as is. If we want to test whether something is less than some value, so again, we have this population value or some hypothesized value, and we want to determine if something is less than it. If I had an alpha of 0.05, what I would do is my cutoff, my critical value here, which determines whether it is or isn't less than, the cutoff here leaves 0.05 left. A little bit better. Down here is the 0.05. So notice that all of that alpha value, all of the 5%, got used up in one area because it's a one-tailed. I am only interested in if it's less than some hypothesized or population value. Okay? Now, if I was interested if it was greater than, I would have used up all the 0.5 on top. So it has everything to do, two-tailed, one-tailed has everything to do with if I'm just trying to determine if something is different, I don't care if it's greater than or less than, I just care that it's different. Then it's a two-tailed test and my alpha gets split up half and half on both sides, which affects how I find my critical values. And then over here in the one-tailed test, I use that if I want to determine if something is less than or if something is greater than one or the other, and that dictates whether my critical value is down here, or I would put my critical value up here if I was concerned with one thing being greater than another. So that's conceptually, that hopefully answers a few questions, but really it probably won't solidify until you see a few examples run through. So let's actually look at a couple examples. I'm going to do one from section 9.1, and then I'm going to do another from section 9.2. 9.1 will use a z-score because we're going to be using population standard deviations, and then the one from section 9.2 we're going to calculate the t, so we'll look at using that t distribution and table instead of the normal distribution table, because we'll be using statistics, or we'll be using sample standard deviation. So in this one, take a look at what I did. California and New York lead the list of average teachers' salaries. The California yearly average is $64,421, while teachers in New York make an average salary of $62,332. Random samples of 45 teachers from each state yielded the following. Okay, so I've got that data transferred down here. So here is reality. So here's essentially how it's going to be working out. Okay, we took samples of 45 from each. Okay, sample of 45 teachers from California produced 64,510, and a sample of 45 teachers from New York produced 62,900. The population standard deviations are indicated here and here. Okay, and here's what it's asking. At alpha equals 0.10, is there difference in the means of the salaries? Is there a difference in the means of the salaries? So here's what I did. I'm comparing these two samples to each other. Is there enough difference? We can see that there is a difference. There's a difference between 65 and 62,000. The question is, they're small samples. So are they different enough to say that there is a difference if you were to look at all teachers? Or is the difference small enough where we really can't say that there's a difference? So what I'm going to do is this. I'm first going to set up my rejection and acceptance criterion. I'm going to set up this normal curve thing. Okay. And here I'm asking, look at my null and alternative hypothesis. My null hypothesis is always in equals. Here my null hypothesis is saying that there is no difference. In other words, these two equal each other. My alternative hypothesis is this statement down here that I'm trying to see if there's evidence for. Is there a difference in the means? So if there's a difference, we would say that mu1 does not equal mu2. So there's our null and alternative hypotheses. So because it's equal to or not equal to, is it different? This is going to be two-tailed because I'm not asking if one is greater than the other or one less than the other. I'm just asking, is there a difference? So because it's alpha of 0.10, I know that that 0.10 has to be split up into the two sides. So we know here's our center, but where now are my critical values going to be? Well, my critical values are going to be at locations that use up 0.05 here and 0.05 here, because I have to split up that 0.10 into two sides because it's two-tailed. So what I'm now going to do is, because I'm using population standard deviations, I know that I can use my normal distribution. So I've got to remember the area of 0.05. So if you look here, I'm looking for the z value here in which the area left is 0.05. So if I look in here and I'm looking at 0.05, remember everything in here is areas. If I zoom in here, 0.05 is right between those two areas, 0.0505, 0.495. So I notice that the z-score there is negative 1.64 to 1.65. So I'm just going to do halfway between those, 1.645. So that's going to be my critical values, my cutoffs on each side, positive and negative. So negative 1.645 and positive 1.645. So what these are the regions that we've identified that said if we are beyond those points, then we're too far away from the middle, which means that there is a difference. However, if we're within that, it means there's a difference, but not enough to conclude that there really is a difference. So what we've done here is, if you look in your textbook for section 9.1, here's the method to calculate your z-score when you're comparing the difference between two means. So I've taken all the numbers and I've plugged it in, and I ended up with a z-score of 0.95. So 0.95, if I look at this normal curve that with my critical values that I put on each side, 0.95 lies somewhere right here, because I'm going from negative 1.6 to positive 1.6. 0.95 is about there. Because that's between my critical values, what I can say is that this right here is not far enough away from my center here. The center here implies that mu1 equals mu2. So the center here implies no difference. A z-score is 0, no difference whatsoever. So yes, there's a difference, but is there a big enough difference to say affirmatively that yes, one gets paid more than the other? And because we set our criteria, our critical values here, because we're between those critical values, we can't say that there's enough evidence. So what we have to do is we have to say that no, there is not a difference in the mean salaries, because our calculated z-score is between our critical values. So again, there is not enough evidence to support the claim that the means are different. There is not enough evidence because we're too close to the center here. These were the critical values. We said if we get further away from that, then yes, there's a difference. But we're not. We're within that region of saying here's normal variability. There's always going to be a little bit of a difference, but that's not enough to say that there's a full population difference. So because we're between, we're going to say, nope, there's not enough evidence that there's a difference in the means of the salaries. However, if our z-value ended up outside, so let's say at maybe 2 or negative 2.5, so we're outside, then we would say, yes, there is evidence to indicate that there is a difference of salaries because we are outside of those boundaries that we set for ourselves. So again, there's always variability, but is the variability between the two big enough to say there's an actual difference? And that's what those critical values do. Let's look at another one where a one-tailed test is used, and we're going to be using sample standard deviations, which means that we need to use the t distribution instead of the n. So, age of gamblers. The mean age of a random sample of 25 people who are playing the slot machines is 48.7 years, and the standard deviation is 6.8 years. The mean age of a random sample of 35 people who were playing roulette is 55.3, with a standard deviation of 3.2 years. Can it be concluded at the alpha equals 0.05 that the mean age of those playing the slot machines is less than those playing roulette? So again, our null hypothesis is always that there's no difference. So mu1 equals mu2. However, in this case, our null hypothesis, our alternative hypothesis isn't going to say mu1 doesn't equal mu2 because we're looking for something specific. We're looking for the mean age of those playing the slot machines, which is 1, so mu1 is less than those playing roulette, which we've identified as 2. So we're curious, is mu1 less than mu2? So here's a situation, okay, in which we are going to be using a one-tailed test. So again, in the middle here, this assumes mu1 is equal to mu2, means there's no difference whatsoever, okay? And we want to know less than, so that's down below. Now, because it's a one-sided, one-tailed test, all of the 0.05 gets used up in this one region. It doesn't have to get split between both sides. So 0.05. Now, if we look at the t distribution, because we're using sample standard deviations instead, we'll notice that there's this difference between one-tailed and two-tailed. Well, I'm doing a one-tailed test, and my alpha is 0.05. So this is the column that I need to be in. One-tailed alpha 0.05. However, which value do I pick depends on what my degrees of freedom are. Now, if you look in your textbook in that section of 9.2, it'll show you that your degrees of freedom are always the lesser of n1 minus 1 and n2 minus 1. So we know that n represents the sample size. The sample size of n1 was 25. The sample size of n2 was 35. So the lesser is the 25. 25 minus 1 is 24. So that's my degrees of freedom. So going back to the t distribution, here is the 24. And I believe I go over to the, second column, one-tailed alpha of 0.05. So it looks like 1.711 is going to be my cutoff value. But because it's on the lower side, I'm going to use a negative 1.711. So going back here, my critical value, my cutoff value is going to be a negative 1.711. So anything above that value is going to be close enough here to say, nope, there's no difference. Anything less than that critical value, that cutoff value, we will say, yes, there is enough of a difference to officially say that those playing slot machines' age is less than those playing roulette. So, again, there's a formula to calculate the t, and that's what I've done right here. I plugged all the values into the formula, and I got a value of negative 4.509. Well, negative 4.509 is way below negative 1.711. So, because it's way below, I can say I'm a lot further away from this middle point right here, which indicates no difference. I'm a lot further away than my cutoff point, so I'm going to say that yes, there is sufficient evidence to show that the mean age of those playing the slot machines is less than those playing roulette because my calculated t value is less than my critical value that I calculated. So again, to summarize that, less than, yes, because my calculated t-score is so much less than that critical value, which was determined from my alpha level. So hopefully that kind of helps square a few things away and gives you a better idea. So after you watch this, go ahead and give some of the other problems a try again. If you have more questions, please feel free to let me know.